Yep, so thank you very much for the introduction. As mentioned, I'm a UMETSAT Fellow, so I work on microwave images at ECMWF under this fellowship programme. And I've been focusing on the use of skin temperature increments from microwave observations and putting these into our coupled atmosphere ocean model. So firstly, I'd like to give you a background on microwave images at ECMWF. So at the moment, we assimilate three sensors, summarise from F17, GMI and AMSR2, and in the near future we will start assimilating summarise from F18. And we assimilate these under what we call all sky conditions, so this means clear plus cloudy conditions. And we can see from this impact graph on the side here that we have very few for a small amount of precipitating scenes, we actually see a very large impact on the system. So this is kind of a measure of how sensitive the forecast is to these particular observations, and this is for AMSR2. So it's really important, basically, these all sky observations and using these at ECMWF. So just a little on the history of all sky simulation at ECMWF. So we started off in the 80s and 90s looking at the assimilation of temperature profiles. We then moved on to assimilating radiances, those sensitive to temperature, humidity, wind speed, and then in 2010 we started the all sky simulation framework, which I've just mentioned. More recently we've been looking at sea ice simulation. So this is some work that my colleague Geer has done, so generating a sea ice model directly from AMSR2 observations and using that within the system. And then the work that I'm looking at is the skin temperature, so generating skin temperature increments from microwave observations and then using those in the system. In the future, we plan to move on to other variables. So a little bit of background on what I'll be talking about today. So in a couple of years, so it's all work that's been going on at the moment, but it takes a while to get into operations. We will be starting to use a coupled atmosphere ocean model. So this is where the trajectories between the atmosphere and the ocean are coupled. So information from the atmosphere can be passed directly into the ocean. This can be used to update the ocean and then pass back into the atmosphere. We are looking at the exploitation of the information from microwave images. So we do this by generating skin temperature increments within the atmospheric system and passing these increments into the ocean. And we found quite early on that to do this, we require these low frequency channels, which most people here will be aware of, that for good information of the surface over the ocean, we need to use as low frequency channels as we can get. So 6 and 10 gigahertz here, 6 and 10 from AMSR2 and 10 gigahertz from GMI are being used in the work that I'll talk about today. And this is really important, not only for just updating our model and making things as good as we can within that, but also for upcoming missions, which are also carrying low frequency channels, such as SIMA. So why is ocean skin temperature important within our system? So firstly, let's have a look at how it's used. We take in Ocean 5 is our ocean simulation system, and Ostia, so we're taking a combination of these two products. We then apply and these are foundation SSTs. We then apply skin temperature parameterization, which uses a warm layer and a cool skin effect to get our skin temperature valid at the time of the observation that we're looking at. We then pass this skin temperature into our observation operator, and from that we can generate simulated radiances. So our simulated radiances are very important because they are what allow us to directly calculate our departures when compared to our observations. But if we add just 0.2 Kelvin to our input skin temperature, we find that our simulated radiances can also jump up by quite a lot. So here I'm just showing the difference in the simulated brightness temperature if we add this 0.2 Kelvin to the skin temperature, and this is all under clear sky conditions to avoid any other factors coming in. And I'm showing this as a function of the skin temperature, so that we can see that for the 6 and 10 gigahertz channels, we really see quite a large increase due to this this small amount of error, we could call it, in the skin temperature. So this really drives our reasoning for wanting to improve these. Even if we didn't then use the information in the coupled system, we'd still want to improve our simulated radiances as much as possible to try and drive down the errors in those and reduce the departures. Because the departures are what basically drives the data assimilation and provides the initial conditions for the forecast. So when we first started looking at 6 and 10 gigahertz, we found that there were quite some interesting quality control features that needed to be addressed. So this is just before we've done anything. And here we can see, so we have AMSR2 6 gigahertz, 10 gigahertz, GMI 10 gigahertz, and then just an example of AMSR2 18 gigahertz just for comparison. So in both 6 and 10 gigahertz, particularly in AMSR2 because of its orbit, but also present in GMI, we see sunglint features. So these are large streaks going down the orbits where we see contamination from solar input, basically. We also saw large RFI signals over Europe in AMSR2 10 gigahertz, which I'll show in more detail in a moment. And in each of these, although I've only highlighted it here in GMI, we also see the impact of cold air outbreaks and potentially emissivity issues with the emissivity model. So I'll explain each of these in detail, but firstly, let's have a look at the coastlines, which I can't show on something this global, but we could show it if we zoom into Europe, for example. So basically, the footprint that we use to screen the coastlines at the moment is the 10 gigahertz footprint, and the 6 gigahertz is much larger, so we're more likely to capture areas of land within that footprint. So what we had to do was adapt our coastline screening so that for the 6 gigahertz channel, it's using the 6 gigahertz footprint. We found that if we do this, we manage to eliminate these high background departures around the coastlines, and this all adds up over a month to reduce the high departures that we see in these areas. So moving on to the sunglint screening, here we can see the background departures for AMSR2 channels, the 6 gigahertz channel, and then we can see that the solar glint angle corresponds to these areas of high departures, so with blue being the zero, basically. So this is the angle between the sun and the sensor being very low. What we needed to do here was not only calculate these glint angles, but also find a threshold at which we should be screening. So if we just add up the departures per solar glint angle, we find that once we get below about 25 degrees, we start to see our departures going up quite significantly compared to previous, to anything above that. So we decided to screen on below 25 degrees glint angle and just get rid of these areas that are affected. Sorry. Right, moving on to the RFI signals that we saw over Europe. So here I'm just showing a portion of the area affected. And we have these large scar marks which are going down across Europe. So there's this very significant one here that we see going through the UK and down off the coast of Portugal. And what we did here was look at the glint angle between the a theoretical sensor, which I'll explain in a second, and the sensor of interest, so AMSR2. So these theoretical geostationary broadcast satellites have been placed at 1 degree longitudinal spacings around the equator, and from that we could calculate the glint angle. For anywhere where that glint angle was below 3 degrees, I've summed up and made an average of the background departures. So here we can use this to find the peaks that we show here, the 30 west, 13 east, and 38 east. And from these peaks, we can say that there's potentially a satellite operating in this area, this longitude, which is causing some RFI contamination of the MSR2 signal at this point. So from this, we could then set a particular set of geostationary theoretical satellites and say at these points we think there is something. Use this to calculate the glint angle within the ECMWF system and then screen out based on this. So again, we use a threshold of around 20 degrees. And we can actually match these up to particular patterns. For example, that one I was describing that goes through the UK is potentially from a satellite operating at 13 degrees east. So moving on to the cold air outbreak signal that we were seeing, we found that there are these areas of high background departures which are extending beyond the areas previously screened out for cold air outbreaks. So this area here where it's blank is where we had some screening out before, and you can actually see that down here we've got the 37 gigahertz background departures, and we do not see this extension coming out here. These areas coincide with largely negative air minus C temperature differences, as well as high wind speeds. So our assumption here is that these may be that 6 and 10 gigahertz are slightly more affected by cold air outbreaks in terms of the signal that we see, but it also may be due to issues with the emissivity model, particularly as we see this at high wind speeds. So if we look at the background departures after screening, here we have some monthly averages. So for July on this side, January on this side, and we have 6 gigahertz on the top and 10 gigahertz on the bottom. So for the most part, we don't see any effect of the sun glint or RFI, but we do still see some effect from these cold air outbreak regions. So here to the south of South America, and in January, up near the Arctic. So there's still something going on there. And you'll see in a moment, these actually translate into our skin temperature increments, but unfortunately, there's not much we can do at this moment about addressing these issues. So let's look at the skin temperature increments that are generated through this process. So these are generated using a sync variable approach. So basically, we add the skin temperature to the control vector, along with pressure, relative humidity, wind vectors, etc. And we allow it to vary within the outer loops of the system. So this is basically trying to find the correct answer for the skin temperature. And the increments that I refer to are the difference between the final skin temperature that's generated through the 4 different outer loops and the initial background skin temperature. Apologies, I seem to have started coughing a lot during this presentation, which is not ideal, but we'll keep going. So if we look at the skin temperature increments, we're going to look at firstly July 2022 and then January 2023. And on the top, we have daytime observations. So for AMSRT, this means observations plus or minus 2 hours around 1:30 p.m. And for nighttime observations, so this 12 hours earlier. So the idea of splitting these up is that we have our daytime, which can be linked to diurnal effects from skin temperature parameterization, roughly. And then nighttime, we can roughly link these to differences to the input foundation products. So here it's important to explain that the input products that are coming into our system are they're SST products which are generated, and then we take them into our system, we do things with them, and so there's quite a delay in the processing time that that happens between what is going into the system and the time at which these observations are taken. So some of the things we're seeing here are potentially related to that difference in the observation time. Basically, we're updating the skin temperature so that it's more valid for the time of the observation that we're using. So a key feature that we see in all of these plots I'm about to show are the cooling features that we see in the Eastern Tropical Pacific, which are in the areas of tropical instability waves. We also see in July, but not in January, not in this next slide, this large cooling pattern between Africa and South America. So we're seeing lots of different features here. There are a few things that we haven't explained yet, which I would be very, very interested to hear people's opinions on today. So just have a good look at this slide. For example, we don't know exactly what's going on here or down here by Australia. So any suggestions are very much welcome. And then if we have a look at January 2023, so again, split by daytime and nighttime, we again see this large cooling pattern, which I will show a bit more detail on in the next slide. But we also see these are residual warming effects, possibly related to model errors or to the emissivity model, as I was talking about just now. So these are the increments that will be added into the coupled system. So focusing a little more on this tropical instability wave, so just showing an example of this here to remind us. What we're seeing is in our background skin temperature, we have this wave, and here in our final skin temperature, we're seeing that it's starting to move across. So this is just an instantaneous example for one day. But if we look at this across a month, we can average this, and we find that we have this red initial skin temperature here and the blue final skin temperature. And we find that there's this shift in the waves of about 0.8 degrees to the west. So if you assume that these are moving at 1,000 kilometers a day, we find that this is consistent with an input SST delay of about 2 days in the products, which is about the difference between what it's coming in to when it's used, which can be somewhere between sort of 27 and 69 hours. So we find that this information demonstrates that our skin temperature is being updated how we expect it to be. And it also gives us confidence that we're seeing meaningful updates from the microwave. So stepping back a little, I just wanted to show an example of why 6 and 10 gigahertz are really important in this context. So here we have an experiment where the skin temperature increments have been generated without using 6 and 10 gigahertz versus an experiment where they've been generated using it. And there are two key differences here. One is the magnitude. Here we have up to about 0.15 degrees increment. And here we have up to 0.6, so they're much larger if we use the 6 and 10 gigahertz. Secondly, without using 6 and 10 gigahertz, we see that there's no discernible pattern, whereas when we do use 6 and 10, we see these strong equatorial cooling going on. So that really gives us confidence that we're doing the right thing by including these channels. So finally, I've just got a couple of slides looking at the coupled atmosphere ocean system. So firstly, to explain it, and then to show some results from it. So this is courtesy of Phil Browne, who is the person at ECMWF who's been implementing all of the coupled information, the coupled system. And here we're showing the coupled trajectories with the atmospheric part, and here with the ocean model. So The skin temperature increments that we've just been talking about are generated within the atmospheric part. And then in the first loop, so there are two loops that are relevant to NEMOVAR, the first and the second. In the first loop, in situ and altimeter observations are added into the ocean, as well as in the second loop. But once the skin temperature increments that we've just been discussing have been generated in the first, between the second and first loop, we can then add these into the second loop as SST information straight into NEMOVAR, which is a 3D variational assimilation system, which uses incremental analysis update to generate an updated ocean status. Sorry. So the ocean is updated at this point using the SST information from the skin temperature increments we've just seen. And then that is fed back into the atmosphere through the next alpha loop. So that ocean is then directly seen in loops 3 and 4 of the atmosphere. There is an option to reinitialize or to cycle. So the reinitialization means that every 24 hours we would take in an external data product, and this is the way in which we're doing it at the moment. Cycling would mean that we only take it in once at the start of, the start date of our experiment, and then not reinitialize with any external information. But we found if we do that, we have the ocean run away quite quickly on us. So at the moment, we are sticking with reinitialization. So we're always taking in the external data sets every 24 hours. So this is the plot I'll show demonstrating the impact of these skin temperature increments in the coupled system. So for those of you not familiar with how ECMWF demonstrates improvements, this is basically, we look at the change in the standard deviation of the background departures. So for any observation system, be it a satellite system or here the in situ ocean observations from Argo floats, if we reduce the standard deviation in the background departures, we then say that we've seen an improvement. It's essentially saying that the fit of the observations to the model is better. So anything on this side with the smiley face of the vertical line is an improvement, and here we're just showing the statistical significance of these points. So we can see there's so an improvement of 0.1%, which is quite significant actually in the ECMWF system. We don't often see large improvements of several percent, for example. So we see this very convincing and quite large improvement in the fit to the Argo floats. And this is both at the top of the ocean, where the skin temperature increments that we've been using would be most appropriate, but also propagates down to around about 100 meters. So this shows that the information that's being passed into the ocean is then being used by the ocean model to improve layers further down. So we're happy with this, and we think that this shows that these observations can really improve our ocean analysis and hence the overall forecast. So just to summarize, we have the microwave observations being with primary sensitivity to the surface being used for the first time. So this is 6 and 10 gigahertz. We're creating meaningful skin temperature increments from these observations, and we can use these in the coupled system to provide a better fit to ocean observations, giving us confidence that the ocean has been updated as intended. And each of these will be included at cycle 50R1, which will be operational in the next couple of years. And finally, everything except the information on the coupled system has been written up into this report, which is available on the ECMWF website, and a couple of papers will be written summarising some of this information. And the coupled system I'm currently writing up, so that should be available soon.